Dear friends, this is the part 4 of the Time Capsule project presentation of the Sri Lankan Geotechnical Society for the ISSMGE. In the part 4, I will talk about mitigation of landslide risk by multiple measures. In the part 3, we talked about by drainage measures. So in part 4, we'll talk about multiple measures, taking some case histories from the Southern Expressway, Ginigathena and Kahagwal. I am Professor Atula Kulatilaka for the Sri Lankan Geotechnical Society. As discussed in the part 3, Professor Karl Tersage said that if a landslide has started to move, the means for stopping it must be adapted to the process which started the slide. So we should investigate and find out the reason for failure, and in our countermeasures, attack the very reason that initiated the failure. So in the last part, I talked about our experiences in stabilizing the landslides by modification of the slope geometry and drainage. In some sloping grounds, further external support in the form of earth retaining structures or internally stabilized systems such as soil nailing or anchoring would be necessary in addition to the drainage measures. So these are some examples, some of our experiences. So this particular cut of the natural slope had to be done to provide path for a bypass road in the construction of the Southern Expressway. There was this house at the crest of the slope. So if we have cut it to a normal gradient that the soil can withstand, the house will have to be removed. So by constructing a gabion wall at the top and providing surface drainage to efficiently run off the rainwater, right? We were able to do the cutting, construct the necessary road while keeping the house there as it is. The surface of the slope was protected by vegetation. This is another example. I have earlier mentioned that our slopes are quite stable during the periods of dry weather due to high prevailing metric suction. So this is the Colombo-Katunayake Expressway. Above it is the Nigambu Road, A3 road, so which is a major road. So this cut has to be made across this major road for the construction of the Colombo-Katunayake Expressway. You can see these cuttings were done without near vertical cuts were done without any problem during the periods of dry weather. But there are buildings close by, and this slope will remain stable if the weather remains dry. But that is not the case in natural, right? So when rainfall occurs, there will be erosion, loss of metric suction, and failures, as we have seen in many places. So in this case, the cutting was done during the periods of dry weather, taking advantage of the high metric suction. Mass concrete retaining wall was done with weep holes and all the drainage measures, and there was surface drainage at the back of it, and the protection was provided for all seasons with this construction. This is again construction that we have done at a number of places. There are unstable slopes in the premises of schools, hospitals, etc. So we have done the cuttings during the period of dry weather, got to the hard surface, near vertical surface, maybe about 70-80 degrees inclination, and by placing the geotextile and the drainage layer, retaining wall, random rubble masonry or mass concrete retaining wall is done with the back batter. So our analysis shows that when you have a back batter, the retaining wall design can be highly optimized. So you can see the weep holes in that. The geotextile placed at the back of it can be seen. So we can find a period of dry weather, and this construction can be done, ensuring the stability of this near vertical cut, and then protecting it for all seasons. Another activity that we have used quite often is soil nailing. So in unstable slopes, after providing drainage, we have installed soil nailing. That is, as we know, is installation of a reinforcement in a drilled hole at appropriate spacing to an appropriate design length. So soil nailing is a passive system where the tensile loads in the nail will mobilize when the slope starts to move. Anchors, on the other hand, is an active system where the installations are pre-stressed. But in Sri Lanka, we have mostly used soil nailing up to lengths of about 12 to 16 meters. As seen by this modified Bishop's equation, when the slope starts to move, tensile load will mobilize in the reinforcement. So that is with a plus sign in the numerator. So that is increasing the normal stress, with a minus sign in the denominator, decreasing the shear resistance to be mobilized to maintain the equilibrium. So both these will ensure the factor of safety will be increased. So we have done our designs installing different patterns of soil nailing. To protect the nail from corrosion, so it is placed on the center of the borehole by use of centralizers. This slide shows the construction sequence of that. So this is a slope which found to be unstable after the excavation. So it was stabilized by a soil nailing arrangement, drilling the hole and installing the reinforcement bar and grouting with a tremie pipe starting from the bottom, and then connecting the nail heads with reinforcements, and just very simple reinforcement was placed for the surface, and the surface was shotcreted. So this is again another failed slope in the Southern Expressway. Cutting was done, but the drainage measures were long delayed. So as a result, the slope failed. So this is a zone where there is a lot of in a valley where there is a lot of water coming from the adjacent slopes. So in addition to the nails, the surface drainage has to be improved at that area. So this shows the basin drain constructed to collect water coming from all the directions, and how it was diverted down through this cascade drain. The nailing was done, and the nail heads were connected by shotcreting. Later on, we try to avoid shotcreting as much as possible. So in the stabilization of these slopes in the Kandy Mahayangana Road, you can see here the nail heads were connected by beams, and in between, and also the nail heads were connected by a mesh of particular tensile strength, and jaw grids, the jaw textiles made up of coir were used, and vegetation was introduced through hydroseeding. As discussed in an earlier presentation, so we do the hydroseeding and protect the seeds till they are grown with the jaw textile made up of coir. So here you can see the cutoff drain done at the crest of the slope. Just next to it is closely fractured rock. I talked to you about high variable conditions in the sloping grounds in Sri Lanka. Here it has weathered sufficiently so that we can grow this vegetation. We can introduce the vegetation. But here it is with much less weathering. It is closely fractured rock here. So the nails here were connected by the reinforcements, and the surface had to be shotcreted. So this is another example of protecting a sloping, unstable slope in a school in Kandy, Mahamaya College, Kandy. So the nail heads were connected by the beams. You can see the reinforcements in the beam. This is the initial state of the slope. So during the construction, now the beams are completed and vegetation was introduced in between. So this is after the growth of vegetation to some extent. So at this stage, it looks like a natural slope. So with further growth of the vegetation, it will appear as a natural slope, aesthetically much more pleasing than a shotcrete surface. We use that that technology in the Kandy stabilization of about 18 failed slopes in the Kandy Mahiyangana road, highly sort of popular highway towards the in Sri Lanka. Now here you can see the nail heads. And in this case, we use concrete pillows, concrete nail heads designed to prevent local failure here. Right? You can see the adjacent site. Because of that site condition, we could not use this technique. We had to shotcrete it. So here you can see individual nail heads are connected by tensile steel mesh with a particular tensile strength. And then with the help of hydrofreezing technique and coir geotextiles, vegetation was introduced. You can see further details of that. So you can see here clearly the nail heads, a concrete block, nail head, concrete nail head, and then the steel mesh connecting all the heads, that is preventing local failure, is seen here, and the coir geotextile is also seen here, and you can see vegetation is slowly coming up. So further pictures of the same road, right, in certain parts of the highway, so we had to use the shotcreting, but many other places we managed to attain the stability with nail heads connected by the steel mesh, and introducing vegetation in between. The toe of this particular slope, shotcrete was used. Everywhere else, it was covered with vegetation. At few places, we use this metallic spike plate. This spike plate instead of the concrete nail head. So it is much quicker, but with the metallic spike plate, the load coming onto the mesh, steel mesh, is much greater. So to prevent the shear failure, the punching shear and the general shear failures in between, we have to use a tensile, you have to use a mesh of a greater tensile strength. So therefore, this was not used very much in Sri Lanka. We have always gone for nail heads connected by beams or isolated nail heads made of concrete connected by the tensile, high tensile wire mesh. Right. This is again another interesting case. You can see here the surface drainage measures were provided. There were berm drains and cascade drains. So this is in the southern expressway of Sri Lanka. This initial tension crack was seen around 9 o'clock in the morning by the expressway engineers. I presented this case earlier as well. And then they suspected that a failure may happen at any time. So the road was closed. So now this actually happened due to some faults in the maintenance of the surface drainage system. So you can see before the failure, right? So this, with that initial movements, these drains have sheared, and by 5 o'clock, the catastrophic failure occurred. Now here you can see the depth of failure surface is not very large, right? Quite shallow, and the surface is not very wet, right? So the back analysis showed that this happened due to the infiltration of water through the relic joints in the system and loss of matrix suction in there, right? So there was no rise of ground water table witnessed with that. So matrix suction was completely lost due to the drainage of the infiltration of water through the relic joints. So the surface that left behind by the failure was unstable. So it has to be rectified. So we used multiple measures there. The steep escarpment was rectified by use of soil nailing. At the top level, we needed reinforcements of length 16 meters. So they were later replaced by, instead of soil nailing, we used anchoring there. And at the toe, put up a retaining wall, toe retaining wall. So that is the road area. So all the debris was removed. This toe retaining wall was done and backfilled. So with the toe retaining wall, we were able to optimize the design of the nailing system. So the ground water table was low, but we introduced certain number of subsurface drains here because our analysis shows that if the rainfall continues for some time, the water table would rise, especially near the toe. So we installed surface drainage, subsurface drains as well. So this is a design drawing for that. So these were the proposed subsurface drains. So this is coming into this trench drain, the gabion wall at the top, right? So this shows the initial slope profile and the failure profile is shown by that. So it was cut back to this profile. 16-meter long reinforcements were installed at the top level. At the bottom level, it was 12-meter long. So later we decided to use anchoring for these longer nails, no longer reinforcements, and these remained as nailing. So some construction activities, the nailing could be installed by this cage mounted on a crane, but for anchoring, we need a strong platform. So this shows the nailing work. And that is the platform done for anchoring. So this is anchor installed with the faceplate and being tensioned. And surface was shotcreted. Now, there were some interesting observations during the construction. When the drillings were made for the nails, we met many boudinage structures, as you see, as can be seen here, right? After drilling to some length, you meet rock, but soon after a few meters, there was no rock, right? So it is going through the soil, and then again you may encounter another rock. So these we refer to as boudinage structures. These are in this metamorphic terrain, the panacetic type rocks which remain unweathered, while everything in the surrounding gneissic type rocks have weathered. So this was an interesting feature in that. Also, another thing that we observed is with the geological mapping, we found that there are relic joints like that, about 2 planes of relic joints, one oriented that way. And in the construction, when the drilling was done for the soil nails, there was water gushing out of these drill holes. So some rainwater had been trapped in these holes, right? They were under some pressure. So with the drilling, so water was gushing out. You can see this worker has covered in mud. This worker who was involved there had been covered in mud due to that water coming out. So the other aspect of that is all these drill holes that we do for nailing are interconnected, right? So when we do the grouting, So when we grout a particular drill hole, so water was moving through those relic joints to other holes. Right, the volume of grout used was much greater than the volume that volume of the holes. So indicated the system of drain joints are interconnected, and the grout was coming out from the other hole. So now this rectification process involved nailing as well as surface drains. So therefore, we first did the nailing and did the surface drain, subsurface drainage at the last. Right? So we'll have to be careful about the construction sequence. So if we have done the subsurface drains earlier and done the nailing later, so the grouting work of the nails would have seeped into the subsurface drains and blocked them. So we did the subsurface drains after completion of all the nailing activity. So this is some detailed studies we did that, modeling the infiltration into the relic joints. So without the relic joint, this would be the seepage pattern. So if we model the relic joints and the relic joints are to be filled with weak, high permeable material. So there is a lot of water getting into the slope through that. And when we model that, we could see the factor of safety is deteriorating much faster. So here we have applied the rainfall that triggered the failure. We had the records of rainfall that triggered the failure. So we applied that on the slope that existed before failure and see how the pore pressure changes will happen and how the factor of safety would vary. So if the surface drainage measures were working properly and relic joints were not there, factor of safety will remain just below 1.2 without causing any failure. So this the loss of matrix suction and the deterioration took place with the infiltration through the relic joints as indicated by this line, right, with continued drain under the conditions of the presence of relic joints and no surface and faulty surface drains will bring the factor of safety to a value less than 1. So this is the view of the slope after the rectification measures. The Gabion wall at the top, the nailed slope surface was shotcreted, right? So that is the toe filling. There was another failure by a highway due to unengineered construction. So highway authorities wanted to widen the road, approach road to this bridge. So they did an excavation at the toe, a minor excavation at the toe, without realizing that this is an old landslide. So with that excavation, the landslide got activated, and soon, within about 2-3 days, a heavy rainfall came in. So the failure propagated further up. So then this bridge was also in danger. So NBRO was called up to help in that situation. So we did our investigations. We found further up the slope, there's a marshy area. So that is the bridge, is the landslide body, the body of the whole landslide. And this is a view of the marshy area at the crest of the slope. There was a lot of water stagnant there. So that is providing a lot of water to the slope to make it unstable. The topographical surveys were also done, cross-sections were established, number of boreholes were done along the steep direction, and the subsoil condition was established. So this is the obtained subsoil condition, loose colluvial soil there, medium dense sand, and residual soil further after with the bedrock at a further depth. So that is the bridge area. This has to be, the road has to be widened. Road has to be widened. So we'll have to excavate up to some distance here in this unstable slope. So mitigation measures were planned. So this was the area of that marshy area with high water table. So we have to improve the surface drainage there, lower the groundwater table, and further with subsurface drains, further lower the groundwater table, and with the for the widening, we need to use soil nailing. So this is the sketch of the stabilizing measures that were adopted. 16-meter long nails were used. So these were nails, no anchoring. 16-meter long nails were used at the top with this subsurface drains, right? And the construction was done in stages. Stage 1 up to that is excavation, nailing, and so forth. But before the nailing, the surface drainage was done to lower the groundwater table, right? Same here, right? So this is the kind of reinforcements that were used for that purpose, right? So this with 3 berms, berm drains, subsurface drains, and the soil nailing stage by stage with the top-down construction, right, to ensure stability throughout the work. As I said before, construction was done in 3 stages. Stage 1, excavation up to that. Before the excavation, surface drainage there was improved. I will show these details later, right? And the excavation along with subsurface drains to lower the groundwater table. After that, move to the stage 2, right? Excavation and nailing along with subsurface drainage, and stage 3. These were some typical arrangements used for subsurface drains, perforated pipes, with sometimes with this metal mesh. And I mentioned that at the top level, there was this the waterlogged area, right? So there were these trench drains done, right? The surface drain along with this trench filled with rubber supported by a geotextile and a drain pipe here. So you can, so that was the first thing to do, to lower the groundwater table at the top level, right? So you can see the construction work, and here you can see how the water was getting discharged through surface drains as well as through this trench drain. Right? I said it is stage by stage construction, excavation for the first stage and nailing, right? The surface drains in position, right? The nail heads were connected by beams, right? So it has now proceeded a little further down. You can see nail heads were connected by beams, right? And then the surface was made here, and hydroseeding was done with the coverage with this the coir geotextile. So the seeds are coming up, vegetation is coming up. So that was a very interesting and a successful story of rectification of a slope with multiple drainage measures. After that, we had a MSc student looking into further details of this, the effectiveness of multiple drainage measures. So in his research, he evaluated the effectiveness of different mitigation measures and their combination, how this combination can make the system very economical. So the methodology applied is with the subsurface model developed, it was validated by modeling a rainfall event and monitoring the groundwater table variation in the boreholes, instrumented boreholes, right? And also by back analyzing the failure that took place with the initial excavation and how it propagated with the rainfall, we could sort of validate the slope W model also to a certain extent. And after that, we analyzed the effect of the nailing and drainage to enhance the stability. So earlier I showed you the stage 1, 2, and 3 constructions. So we analyzed what would happen if a critical rainfall. So this shows the critical rainfall for this particular area. Based on past rainfall records, we establish a critical rainfall. So it is that. So if this critical rainfall falls on the site during the construction stage 1 or 2, what would happen? So if there were, as shown by that, if there were surface drains but no nailing, then the factor of safety would be maintained at a very low level. Surface drains and nailing at a very low level. So if there is no drains and no nailing, it will be much lower. Along with this rainfall, it will be less than 1, meaning it will fail. So if you have done surface drains only, again, it cannot come above 1. Surface and subsurface drains together will maintain it slightly higher. Surface and subsurface drains, but with no nailing, it will be maintained slightly higher. Then with surface drains and nailing, only surface drains and nailing, it will be maintained at that level, right? No draining, but nailing. You do the nailing without any drains. So that is this dots. And if you implement all the design measures, that is surface drainage, subsurface drainage, and nailing, we can maintain a high factor of safety throughout the rainfall event. So that is how the factor of safety of the slope would vary when the nails and drainage is in position during the stage 1 construction. So this is how it would happen in the stage 2 construction. So there again, the critical point to be seen is the full stability will be there when all the measures, surface drainage, subsurface drainage, and nailing are in place. When the nailing is not in place, the factor of safety will be much lower. So we did that for both stage 1, 2, and 3 constructions to see how that will happen. So this is some pictorial view of the failure surfaces obtained. If there are no drains or no nailing, right? So this is the failure surface that would be obtained, that is that value, right? And when surface and subsurface drains are in place and nailing is done under the critical condition, under the critical rainfall, this situation is the lowest one. So that is the potential failure surface, but it is with the high safety margin. So to ensure this adequately high safety margin, we need to have both surface and subsurface drainage measures and nailing. Now, how the drainage measures would economize this was further studied by analyzing what would happen if you install this same nailing arrangement but without drainage. Practically, it is not possible because you can't do these drain nails without lowering the groundwater table. But hypothetically, we studied, say, if we install the nails without lowering the groundwater table, then the factor of safety would be just around 1. So to bring it to an adequate level, we'll have to install more nails, right? The total nail length, this is the actual design that we did, was 1,624 meters. But if we have done the job without drainage measures, you need about double the length of the nails. Spacing has to be reduced and the length has to be increased. Practically, this is not possible because with the high groundwater table, the practical exercise of nailing would be very difficult. The boreholes would collapse when the ground under the conditions of high ground water table. So if only surface drainage measures were done without subsurface drains, again we can see the design implemented will have a lower safety margin. To increase it, you need to do a lot more nailing. So the nailing design can be highly economized when you combine that along with surface drainage and subsurface drainage. The construction activity will also be greatly simplified, may be much easier without any collapse of the boreholes when you have lowered the groundwater table with subsurface drain. So the general findings of that is listed here. This ancient landslide at Guinea-Gassena reactivated due to excavation, and it was stabilized using extensive mitigation measures. Surface and subsurface drainage measures could enhance the slope stability to some extent, but soil nailing is mandatory to achieve the stability requirement and necessary widening of the road. So it is not just to make the slope stable as it is. Some widening is required at the top, right? So that widening is the one which initiated which reactivated the failure. So in that case, nailing is an essential component, and the construction sequence. So we have to plan the construction sequence properly. It must be top down, right? Adopting the correct sequence of drainage and nailing to prevent failure during the construction. And as finally, drainage measures help to economize the nailing design. If the groundwater table remains high, you need a lot longer nails and laying nails at closer spacing. So this is the slope after the implementation of the rectification measures. You can see the vegetation has come up in between the beams that connected the nails, and it appearing to look like a natural slope. This is again another landslide in the main road system of Sri Lanka, in the road to Badulla at Kahagolla, which had been there troubling the road authorities for a long period. So, so that is the main road to Badulla. So it was a slow-moving landslide. So there is the boundary identified, right? So during the periods of heavy rain, so it is moving. So the head of the landslide is further up the slope, right? So this is a normal period. So this is moving down, lifting up the rope, damaging the rope, and disturbing the traffic in that. So a lot of subsurface investigations were done through boreholes and the geophysical techniques, and instrumentation was done. So these are top to down the slope. And with that investigations, the failure surfaces were identified. It is not a single failure surface. It was a composite failure made of different failure surfaces, as illustrated by this plan. The blocks of failure were illustrated in this plan as well as in this cross section. So there were 1, 2, 3, 4 different blocks of failure which are moving down during the periods of heavy weather. So this idealization was done with the help of results of investigations. And some instrumentation results, the groundwater levels measured at different boreholes located, instrumented boreholes located on the axis of the landslide. So with this heavy rain periods, you can see the rise of the groundwater level. Every heavy rain period, the groundwater level rises, then there is lowers down. And the recordings of the extensometers, you can see the different blocks identified. Extensometers were installed across the blocks. You can see 1, 2, 3, 4 here. right? So the movements recorded at these extensometers during the periods of heavy rain are plotted here. You can see that with these periods of heavy rain, right, the movements are increasing, not in all, in most of these extensometers. So it is a slow moving landslide that gets activated during the periods of heavy rain. As you can see, it is well instrumented, and the slope, the failure pattern, the failure surfaces were well established and instrumented. Then with that, stabilizing measures were proposed. So this is the road. The stabilization measures, primarily drainage. There are surface drainage measures. There are various drain types, surface drainage measures, as shown in this plan view. Then subsurface drainage in the form of fan drains here, right? And there were a number of drainage wells, deep wells, and from the well, drilling was done in different directions in a fan-like. Now that is the landslide area. So the water in that area has to be drained. So that was achieved by these fan-type drains done from the surface and from drainage wells. There were 6 drainage wells, and some weight was reduced at the crest, and embankment was done at the toe, right? Remember, one of the first things that we discussed is removing the load from the top and adding load at the toe, and also some anchoring was done. Anchors, series of anchors were done. So you can see it further through this cross section. So that is where the load was removed and it was placed back here. That was the road. So these were the drainage wells. These were the drainage wells, right? From a drainage well, a series of fan drains were done, and the water collected at the bottom of the drainage well was taken to the next one and taken out like that, right? So you can see a drainage well here with this subsurface drain in a fan type orientation, right? And so these are, I said that at the top here, there were subsurface drains drilled in a fan type orientation in different directions over here. So this is a picture of that. So these were different surface drainage measures shown in the plan here. Right? Drainage wells, surface drains, and subsurface drains. And then counterweight embankment below the road level, anchoring above the road level. So this is the completed road, anchoring above the road level over here. So that is the road. So that is the counterweight embankment here, at here. And the removal of soil from here, from the crest, and some protective structures done thereafter. So with that, this slope was made stable, and they are working very well now. Now, another challenge that we had was the rock falls. It is less common in the country, but some places it is a critical issue. So this is the Kandy Mahayangana Road. So this rock, exposed rock, is with joints oriented in the adverse direction. So during the periods of heavy rainfall, pieces can come down, causing much sort of disturbance and threat to the traffic. So you can see this situation, a much more tragic situation. Luckily, no one was injured here. The larger blocks have come down. So this is a grave concern. So we have stabilized many other soil slopes along this road, Kandy Mahayangana Road, but this was delayed due to the lack of expertise contractors in the country. But later on, with Japanese support from the Japanese contractors, we did that. So this view of the jointed mast. Our mapping identified we need to protect it by nailing or by rock netting or rock bolting in this area. So this is how it was after finally installation of the rock net, right? So this netting, the net was drilled in at stable locations. It will prevent any blocks coming out. So it is keeping the blocks as it is, preventing them falling off from their original position. So this is further view of rock netting. And at some locations, we did the curtain netting. So there is this curtain net. So small pieces can come down and be inside the net. So net prevents them coming outer to the road area. So nails the falling pieces are contained there by the rock net. And also at some locations, rock fences were done to catch small size rock falls. Over here, you can see the construction drawing and then the actual work in operation. So the rockfall problems in that segment of the Kandimayangan Road were sort of mitigated with these different site-specific netting measures done there. In conclusion, I would say now, sloping grounds in Sri Lanka are made of residual soils, rocks at different level of weathering, and colluvial soils from previous landslides. Groundwater table there is generally low during the dry periods, and the slopes remain stable due to the prevailing matrices. But with rainwater infiltration in uncontrolled manner, these slopes would be unstable and the failures would occur. The challenges offered by the rain-induced landslide is well taken by the Sri Lankan geotechnical engineers, and we have made good progress in reducing the risk of landslides. Deficiencies in the process, we follow, were identified, and continuous efforts are made to improve. The scope of the landslide assassination project that I mentioned in the second part is being widened now to include the flow part. So not only the initiation parts, now we identify the flow parts and the depositional areas, so incorporate them in the maps. So the whole risk area is identified, and also all these are rain-induced landslides. The number of automatic rain gauges in the country are increased to cover all relevant areas. And we study the recent landslides to identify the rainfalls that triggered these particular landslides. With the current records, with the rain gauges, automatic rain gauges available in many parts of the country, now for more recent landslides, we can identify what is the rainfall that triggered the particular landslide. So we are doing a detailed study to identify the triggering rainfalls, threshold rainfall values for different zones of different susceptibility. We have a design office at NBRO. So we do the design of this mitigation work for landslide and the rectification work for forks which have not failed. The rectification measures and the design measures were done at the design office. So in that, there are a number of graduate civil engineers with postgraduate experience, most of them, and they are guided by senior geotechnical engineers. And we from the universities work in close association with them. And also our team includes engineering geologists and geologists, so who would provide us good understanding about the background geology. When we visit a potential site, a complete team comprising of engineers and geologists visit there to discuss the features noted, observed, and come up with the designs. So in the process, we do the geological investigations, geophysical investigations, and geotechnical investigations through boreholes. Wherever possible, install the monitoring equipment as shown in previous the presentation, previous slides. So we gather all the actual information through this process of investigation and monitoring and come up with a design. Once we come up with a design, the team visits the particular site, with the design in hand and verify the applicability of the design to the under the site conditions. It is not done from a design office alone. I mean, we visit the site many times during the process to verify our design measures. Over the years, institutions such as Norwegian Geotechnical Institute have provided great assistance through many collaborative studies. So NGI experts have assisted in training the NBRO staff on aspects such as flow path modeling, which is currently being done, and also in design of rectification measures. They have also provided us drones to conduct the surveys under difficult ground conditions to obtain 3D terrain model to establish the soft topography. They have trained NBRO staff on this extent. And also they have provided us with modern techniques like ground penetrating radar and cross-bore logging to enhance our investigation capacity. Also, the institutes like JICA have provided collaboration in many work. Now, this Kahagola landslide, they were highly involved in this design measures and also in the Badalusirigama landslide. So JICA experts work together with the NBRO scientists and engineers to come up with these designs. A large number of projects were done within the last 2 decades for the reduction of landslide risk in the country by mitigating the instability of these critical slopes and the landslide along various infrastructure facilities such as roads, railways, schools, and hospitals. These projects were funded by the Sri Lankan government and also through loans offered by different organizations like World Bank and ADB and so forth. There were around 150 sites rectified within the last decade at a cost of about 13 billion rupees. Local contractors were involved in great majority of these projects. In certain situations, we got foreign expertise, but local contractors are involved greatly in most of these projects. So their capacity also has increased. Now, we have to do further work in areas like the monitoring of these landslides globally, right? So we have plans to use the techniques of terrestrial photogrammetry, digital photogrammetry with drones and LiDAR survey and INSA satellite techniques to monitor the landslide. We need to monitor the critical slopes as well as how the stabilized slopes are behaving under different critical rainfalls. Many government organizations such as Road Development Authority, Disaster Management Center, Departments of Meteorology, Department of Education, Department of Health, and civil engineering community in the country have collaborated with NBRO over the years in this national effort to reduce the risk of landslides in the country. So the effort to reduce the risk of landslide in the country will continue with the incorporation of emerging new technologies and with the advice and goodwill of all the different stakeholders. Thank you.